In our argument, we've supposed the two electrons were scattering off one another. But the same conclusion can be drawn for any state of the pair of identical particles where the two particles overlap or interact, including, for example, electrons in an atom or a molecule. We discussed the identical particles as if they were electrons with the same spin, but we've not presumed any specific property of these particles other than that they are absolutely identical. Thus, we could apply the same quantum mechanical argument to protons with the same spin or neutrons with the same spin. We can also apply this argument to photons.
We find that a given kind of particle always corresponds to only one of the possible choices of gamma. All particles corresponding to gamma being +1, that is, with a wave function for a pair of particles in the simple conditions we've considered so far, being of this kind of form with a plus sign in it, are called bosons. Photons and all particles with integer spin, including also, for example, helium-4 nuclei, are bosons.
We say that such boson particles have a wave function that is symmetric in the exchange of two particles. Sometimes, loosely, we say the wave function is symmetric, though the symmetry here is a symmetry in the exchange of the particles, not in the spatial distribution of the wave function.
All particles corresponding to gamma equal to -1, that is, with a wave function for a pair of particles in the simple conditions we've been considering so far, in this form here with a minus sign in the middle, are called fermions. Electrons, protons, and neutrons, and all particles with half-integer spins, are fermions.
Such fermion particles have a wave function that is antisymmetric in the exchange of two particles. Loosely, we sometimes say this wave function is antisymmetric, though again we are not referring to its spatial distribution. Fermions have one particularly unusual property compared to classical particles, a property that has no classical analogue, the Pauli exclusion principle. Very often with fermions, and occasionally also with bosons, we have to consider another non-classical phenomenon, exchange energy.
For two fermions, we know that our wave function is built from this kind of form with a minus sign in the middle. Suppose now that we postulate that indeed two fermions are in the same single particle state. Say state A, for example. Then the wave function would become the following. Psi A of R1 times psi A of R2 minus psi A of R2 times psi A of R1. Well, that's just equal to 0. And that wave function is 0 everywhere.
So, it is not possible for two identical fermions to be in the same single particle state. This is the famous Pauli exclusion principle, originally proposed to explain the occupations of atomic orbitals by electrons. Only fermions show this exclusion principle, not bosons. There is no corresponding restriction on the number of bosons that may occupy a given mode.